all of it last time. Hi, Logan. Okay. Okay. Sorry, my little boy's yelling, doing his nonsense. Okay, so we're going to do our very last lesson today. We're going to give you your last assignment. If you're on track and you're trying to earn the grade bump, this assignment will be part of it. It's actually going to be a lab to do. We're going to end up applied calculus with applying some calculus. Imagine that. And then that'll be it. So chat's open. If you have a question, you can type in there, or if you want to raise your hand, something you want to say, then I can flip over and give you a mic. But let's go ahead and start with a review, from our last class. Kind of catch up or revisit where we were. So last class, we talked about an application of integration, which was an area application. So for example, let's say I had two functions. I had a horizontal line, like y equals 9, and I had a parabola, y equals x squared. And let's say I asked you to calculate the area bounded by those functions. So that sort of, pizza-shaped area or quarter of a pizza-shaped area. And I asked you to calculate that. Ooh, that's my child yelling. So we talked last time about organizing a function, the graph, by looking at a top function and the bottom function. If we kind of thought about doing little rectangles inside here, kind of going from the top to the bottom, and that was going to be part of how we set up our integral, that we would integrate the difference between that sort of the area region. Those would be x values. So at by that x value, which would be where x squared would equal 9, which algebraically is plus or minus 3, but for our graph, x equals 3 is the one that makes sense. And so to calculate that area, we would calculate from 0 to 3 the integral of, hopefully you're thinking this, 9 minus x squared. Because throughout this region, throughout x equal to 0 to x equals 3, the y equals 9 function is greater than the y equals x squared function. Okay. So that was kind of our focus last time, was the idea of how to set up the integral that would calculate an area. And then, not new, but just a reminder, like, oh, okay, so I would then take the antiderivative and I would evaluate the antiderivative at my two limits of integration, starting with the top one plugged in minus the bottom one plugged in, which is fundamental calculus. So that would be a 27 minus 27 over 3 minus 0 minus 0. And so it would be 27 minus 9, or a big old 18. Yeah. And so we kind of, if you look at this, we have built our skills. We talked about the antiderivative part, and then we talked about the fundamental theorem part, and now we talked about how to fit it to a problem situation. What would we use this calculation for? This calculation could give us this area. And now sort of the remaining piece is, what can that area represent? What can we do? What's a problem situation that would have us calculating an area like this? And so I'm going to show you two problem examples. They're similar, okay, in that they both calculate what I'm going to call a difference, okay, cumulative difference. But the word you're going to see that's sort of an economics idea is the idea of a surplus. Okay? The difference between one function model and another function model's outputs accumulated as a surplus. So let me talk to you about what the graph is that I'm showing you here. Let's say we have two different revenue models. That in one revenue model, we'll call it the old revenue model or the original revenue model, our cycle, that our revenues would be accumulated according to this particular formula, where T is the year and year 0 is 2000. Okay, so we're figuring that based on different things, that the amount of revenue we can expect to accumulate or the amount bring in a particular year in T equals whatever would be calculated by this. Okay, and that is that model right there. Now let's say that somebody has come up with some ideas for changing, maybe changing pricing, maybe doing something, whatever, and so maybe an advertising change, whatever. So they're saying that based on their changes, that their new amounts of revenue would be modeled by this function. Oops, not cubed. That would make a big difference. Squared. Okay. So that's the newer model. Okay. And we'll say our revenue is also, just so we're clear, in billions of dollars. Okay. So this is this point right here indicated by the little square on the, and that little square is on the new model, is saying like in year 2010, if we were in the new model, this would be our revenue in billions of dollars, as opposed to whatever, and this graph is already made, so I can't, it's not going to get a new number, but opposed to what that number would be. Okay, so clearly the new model is outperforming the older model. Our newer revenue model has the ability to give us more revenue than the old model. How much more? What is the difference? The cumulative difference. And so let's say that we decide that, and that these models, let's say these are the models where, let's say that in, I don't know, I'm just going to kind of pick a random spot here, and I'm going to say that this is I'm not going to say 2015, I'm going to say t equals 15. So let's say at t equals 15 is the point where we switched models. So we were on the old model path up until 2015. And then in 2015, oh, look, it's like a little, it would be like a piecewise function. We are on the new model path. What we're interested in to talk about is, well, what's that space represent, right? That space represents the total amount of money we will, the total amount of surplus, extra money we will get from following the new, whatever the new revenue model has us doing versus what we were doing in the old model. In the old way, our revenues would have followed this path. In our new techniques or new whatevers, our revenues are going to follow this path. How much more money? Okay. So that's what the yellow is representing. Total extra or gives us. Okay. So let's make a calculation. If I want to figure out how much more money I've gotten, I would have earned, or how much more money I would collect over a 5-year span from, sorry, but sneeze. Oh, I guess that's why I'm at home. So I went, thank you. My little boy loves to yell. God bless you. So if I want to calculate, so if I switch techniques, switch models, switch whatever in 2015, and I'm now accumulating revenues according to this model, how much more money, what's the difference in the amount of money I would have collected? So from 15 to 20, I'm going to integrate the old revenue model, or excuse me, the new revenue model, because that's on top, minus the old model. Plus 0.1 plus. Because in this particular scenario, it's not so much that it's new old, it's the top minus the bottom. Okay. This is the greater function. These function values are greater than these function values in this interval. And so if I want to calculate the difference, I would have to actually have calculated every difference, every new revenue, every old revenue, and subtracted them. This is essentially what this does. With calculus, it lets me calculate what all the old revenue values would be, what the total amount of old revenue would be, what the total amount of new revenue would be, and so what's their difference. But it does it in one big calculation. Okay. I'll just kind of pause for a minute. Any questions on that? I know you weren't given sort of everything, but and I wrote some things out here, but one example of how you would use this. 2 revenue models, in this case, this revenue model switching to this versus being on this model, what's the improvement? So, all right then, no worries. Now we're in simplifying land. I wrote these so they would be pretty for us and our friends. So the 7.21s will subtract away. The 0.26t and the 0.1t will give us 0.16t. And I'll end up with plus 0.01t squared when I subtract my t squared terms. And I will let you, I already did a little bit of calculating. If I did the antiderivatives to this, 1t cubed over 3 from 15 to 20. And ultimately, all that arithmetic is going to come out to be 29.416 repeating. And you're like, 29 what? 29 billion dollars over 5 years. Okay. $29 billion more in revenue. It's not that I'm going to earn $29 billion in revenue. It's $29 billion more over 5 years. That's the improvement. That's the extra. That's the surplus revenue. If I keep going the way I was going, I would be making a certain amount. But if I switch to the new model, over 5 years, I will have made almost 30 billion more, or brought in 30 billion more revenue. Doesn't mean I'm going to make it. That's not my profit. Okay? Because the next person would say, well, what's the cost? What's the change in the cost going to be? And so we would have to look at the difference in all of that to ultimately assess the difference in the profit. Okay. So the difference, cumulative difference, the difference over time between two models. Okay. If my models are revenue models, then this difference represents more money coming in. If I've got cost models, then the space between them is a little different. Let's take a look at this cost problem. You can see this came right out of your text. It says the projected fuel cost, I apologize for reading, in millions for an airline from 2015 to 2025 is represented by that function. But then where 15 represents the 2015, okay? But let's say the airline purchases more efficient airplane engines, then fuel cost is expected to decrease and follow that particular model, okay? So this is the old model. This is the new model. These are costs. So let me go, oops, actually, cut. I don't know where my writing's going to go here. Let me just move these. Okay, there we go. Old, new. Put this right here. Okay, so you can see this is the old model. The dots on the old model, that's what's listed up here. Here's the new model. This is the old cost model. This is the new cost model. Obviously, there's a gap between them. And so if we, in this scenario, calculate the space can represent money saved. If we are following the new cost model instead of the old cost model, our costs are lower. Space will represent money saved. It's the difference between the two models. So it's still a difference, but because of the functions that we're looking at, cost functions, this represents money saved, okay? Versus revenue functions would be money brought in, profits would be money brought in. It just depends on what the two functions represent, okay? It's the difference between the two. It's just, well, how do we want that? What does the difference represent? What are we doing with that money? Okay. Now, so let's say I've got x equals 10 here, and this are supposed to go to 2025. I don't know that I have this, but let's say we make a change next year so that up to 2020 we were following the old model. And in 2021, we make the changeover, we adjust the engines, do whatever we need to do so that we're running according to the new cost model. Assuming that these models are only valid up to 2025, maybe in 2025 something else happens. I don't know, maybe we have like an so much for fuel up to 2025, and then we'll renegotiate that. So for some reason, 2025 is kind of an artificial cutoff. But given that, how much money are we going to save making that change in 2000? And so we might answer this question because we might say, is it worth it? You know, what are we going to have to spend maybe to make the change? What do we have to do to get the more efficient engines? And when we're getting the more efficient engines and reducing fuel costs, you know, is that reduction, is that money saved enough to offset what we had to spend? So in order to calculate that, I would integrate from 21 to 25. And in this case, the old model is, oops, I'm sorry. I kind of put all that together. So try that again. And let's get my pen. Okay, so 568.5 plus 77.51 T minus 525.6 plus 6.43 T. Technically got DT there. It's more of a calculus thing than anything, but that's just sort of an indicator. Okay, so when we make the change in 2021 from 2021 to 2025, how much money am I going to save? And, you know, given, let's say, there's some kind of offsetting cost to make the switch to the efficient engines, maybe there's you know, something we need to do to them, an upgrade, some kind of mechanical thing. I'm just writing randomly. Is it worth making that change? Am I going to profit at all? Am I going to come out ahead? 21 to 25. Let me see. I've got my work, but I'm going to double check it again, making sure. So how about 568.5? Oops. 0.5. Whoops. Whoops. Minus 525.6. Looks familiar. So 42.9 plus 7.15 minus 6.43 is 0.72 T. TT. All right. 715, so let's do stat. Oops, sorry, not a stat. I don't know why I'm thinking stat here. Give me a second. Oops. Good. Checking there, I'm doing this right. Okay. Oh, good. 3784. Okay. So ultimately, hit this with my calculus. So 42.9 T plus 0.72 T squared divided by 2 from 21 to 25. And after it's all said and done, I'm going to get 237.84. What's that? That's in millions of dollars. Is how much money we're going to save over the 4 years. Okay. So is that worth it? Is it good? Well, it depends on what we have to pay to make the change. I mean, if we've got $100 million out of pocket to pay, but we're going to get this much back over the 4 years, then that might be worth it. There's always going to be different factors. And so, the analysis of any of these costs would be what, a person would do to then make recommendations. Okay, what are we going to do if we make a change here? How does that affect other things? There's always going to be multiple variables included in any of these scenarios. Okay. But area between two curves, depending on what the curves represent, area will represent the change from following one function path versus another. Now, a third option, or another option, or what I'm going to ask you to do for your final assignment, is to do an area calculation, actually with two different versions of models, but you are going to create your own models. So let's see, if we look at, let me pull this up. Okay. Let's see if I can share it. Oh, I'm sharing nothing. Okay. Now I'm sharing, hopefully. This. Okay. Okay. So, this is a lab that's going to show us a third sort of calculation of area application. In this case, we're going to look at two different functions. The money coming in, a function that's going to represent the money coming in compared to the money coming out, where the difference between those two functions is going to represent surplus. This particular data happens to be the data from the Old Age and Survivors Insurance Trust Fund, which is the original name for the Social Security Trust Fund. Okay, the idea was the government thought, you can correct me if I'm wrong, but this is my belief that I remember when I've studied it, that the government was like, okay, we need to help people save for retirement. So the idea is we will collect money from them, we will save it for them, and then when they retire, we will give them money back. That way we will help people make that decision to have money when they retire, Social Security. Okay, so you are secure later in life. And so what we have now is a procedure where there is money automatically taken out of your pay that goes to the Social Security Fund. And then when you reach a certain age, you qualify to receive benefits from Social Security. And those benefits are dependent upon what money you put in there, where you are, your age, how long you've worked, and so on. So this is money collected starting in 1990, money paid out. So what I'm asking you to do first is to do our old friend regression. You can do this with your calculator or with Desmos, and if you need help doing either one of those, we can talk about that. I can pull that up right now, or we can talk about it in office hours this week. But you're going to start off with a linear regression model for both of these. So these are your X's, and these are your Y's. That's one table of data. And so you're going to do one regression with these X and this Y, and then you're going to do a regression with this X and this Y and get two linear functions. You're going to show me the graph. You can do that on paper and do it on Desmos. It's super easy to do all the regression on Desmos. It'll graph it. You can have the area shown right there and just, include it or it as part of your answer. And then calculate the area between those two curves. Okay? That's going to represent the amount of money, the surplus money, in the Social Security Fund between accumulated between those 2 years, between 1990 and 2009. Okay. Now, second, we're just going to look at it using a different model because modeling is subjective. You know, what model you use for data. You can use different models, and different models have different values. I don't have the R value asking for your R values here, but I'm going to ask you to go ahead and do a quadratic model for both of those, and then do the exact same thing and calculate the amount of surplus money. Now, then I'm going to ask you to do something. So that's really the calculus part. Now I'm going to ask you to do some thinking. This is a mathematical question. If the models intersect, all right, so if you, I'm going to see if it will let me draw on here. It's not. Okay, so wait, let me do it this way. So I know. No. I was hoping I could figure out how to. I don't know why my. Let me. No, I'm there. It's Haiti. Escape, escape, escape. That just pins it. Why won't it let me go away? Can I just make it smaller? I know you guys are like, seriously, you're super annoying, Mrs. Wilbrock. I know. All right. So I want you to talk to me about what would it mean if the two models intersected and switched places. All right. And then, oh, that's good. Go to this article. Hopefully, we're still, let me go ahead and. Hopefully that link still works because this is a project from last year. I would have been smart to check it. I don't know what's happening now. I don't know where I am. I'm lost in the computer. What's happening? Where am I? Oh, okay, you're not seeing anything now. You're seeing a big bunch of nothing. Let me try that again. Sorry, guys. You're very patient, or you're just ignoring me. Either one. I want to go back to the lab. Oh, Word is not being my friend. All right, we'll just close it. I'll double check the links and make sure that they work. So what you're going to do, let me flip, let me just, and that's not working, that's not working. Okay, here we are. Oh, but it's nothing. Okay. We'll just share that. We'll just go there. Okay. So anyway, what I was showing you on the lab, I apologize, is you're going to talk to me about, actually, I can do this. Sorry. Crazy. Okay. So what I had said was, you know, if you have the money coming in, the receipts, and the money out, you know, what does it mean if the crosses? What if it means if out goes over in? Okay. So that was the part I was trying to draw before I messed up everything. Okay. Then the last two parts of it are going to ask you to look at, cancel, are going to ask you to look at, cancel that, cancel, just back to here. I don't see how to undo that. Okay, so it's just going to ask you to look at some websites and kind of talk to me about what you see on a couple graphs on one of them. I will double check, and then read two different articles about Social Security and just respond to, you know, what's one thing you read in there that was interesting. So you can't really give a wrong answer because there's not a wrong answer in terms of what you felt was interesting. Okay, so that's going to be your final assignment. I will make sure the links in that document work. Let me double check that. Double check it. Let me make sure the links in the document still work, and then I will get that posted for you. And then you can work that through. Like I said, come see me in office hours tomorrow from 11:30 to 1. Come see me in office hours on Friday from 11:30 to 1. If necessary, you can always last minute talk to me in class about any aspect of the assignment project isn't working out. And I would like to have that assignment turned in, so I'll be willing to talk to you about it in class, definitely no later than 6 p.m. on next Tuesday. And that puts us in the situation where I'm then able to start calculating final grades for seniors, and we'll go from then. Senior grades will be finalized and fitted by the end of the week of next week. Okay. Like I mentioned earlier, if you didn't hear this, be on the lookout for emails about collecting materials from seniors and other senior activity sort of things. I think they're going to do it sub-school wise. So, you know, Daviana, you're going to be kind of earlier in the world, and Keely, you may not be till kind of the end of the week. I think we're going to do like Wednesday, Thursday, Friday next week to start for seniors. Let me know if there's anything else you need. That's all I've got for today, other than that little hot mess where I couldn't show you, but I will double check your project and I will get that posted up for you. Thanks for coming to class. I appreciate it. Let me know if you need anything. Good luck on the rest of your AP exams, and I might see some of you next week at school. I'm going to volunteer to collect things, so if I see you, great. Hopefully I'll be able to give you like a little virtual high five, virtual hug, and tell you congratulations because you're almost done. You have almost graduated. You're super close. Okay? All right. That's all I got. Peace out. Wash my gang signs. I'm done for the day. Have a good afternoon. Have a good rest of your week. Let me know if you need something from me. We'll talk soon. Oh. Well, I don't know. You just did you look at the turn-in slots, Daviana? You're welcome, Logan. I'm sure you can figure something out. I think they're going to be like from 3 to 7, and if it doesn't work out, you can contact your sub-school principal or whatever. So, oh, okay. Well, hey, that's okay. Florida's good too. What part of Florida are you in? My husband's family lives in Vero Beach. His mom and 3 of his siblings. Okay, he loves Tampa. That's where he wants to build a retirement home so he can watch the Yankees in spring training in Tampa. Okay. All right. Well, don't worry about it, Daviana. We're going to be there. You know, you're not going to be the only person that's not going to be able to bring their stuff. So it's all good. So take care. Have a good one. Let me know if you need something.